Hello, general biology students. This is week 5 in general biology, and we need to continue our discussion on chapter 2. We did some chapter 2 notes last week, especially on electron configurations, atomic structure, and bonding. We want to piggyback onto that in chapter 2 with this bonding of the water molecule. And in this section here is strictly all water that we want to talk about. So let's jump right into the water molecule. Water, hey, I don't have to tell you this, how essential it is to life, but I do need to review these bonds right here in this graph. Remember, the water molecule is an oxygen molecule, which is indicated in red here, and the two smaller blue molecules. Remember that Mickey Mouse appearance to the bond here. This is the water molecule, H2O, one oxygen. But remember how we talked about oxygen is really greedy. It has a high electronegativity. It attracts the electrons that it has and the electrons of hydrogen towards its end of the molecule. So the red end of the molecule is slightly negative. This end over here where the hydrogen are at is slightly positive. It's like a bucket full of magnets. You can't pull one out without pulling all of them out because all of the molecules, all of the magnets are attracted to each other. That makes for some crazy characteristics for water that are essential for life. That's why it's the universal compound on Earth that we have to have. And so let's look at some of these properties of water, these hydrogen bonds that are found here between each water molecule. This one and this one, this one and this one. They're all bonded by hydrogen bonds. Well, let's look at some properties that result from that make water an extremely unique compound. First of all, water is what we call a cohesive element or a cohesive molecule. By cohesive, we mean all of these molecules are attracted to each other. That magnet effect, that's what we call cohesion. It's the tendency of water molecules to be attracted to each other. They stick to one another. They are cohesive. Now, what that does is it creates what we call a very significant surface tension on bodies of water. I mean, I know this sounds really hokey here, but water has such a strong attraction to itself, creating a surface tension that ships made out of iron don't sink. I mean, think about that. There is such a strong surface tension between these water molecules that it causes things to float. And some animals, even like a water strider here, can literally walk across water because they have certain features on their feet that spread out and they take advantage of this surface tension of water. So this cohesive property of waters is important for just human economy and just life on Earth. And but it's all this surface tension is a result of the cohesive properties of water molecules. But water molecules are also adhesive. Not only are they attracted to each other, but they're attracted to other surfaces. When you get in the shower, you get wet because water is attracted to the molecules of your skin cells. A straw that you suck on in a restaurant, water is attracted to the sides of that straw and move up just because of water. I mean, when we were kids in the 60s, we didn't have gas stations on every corner. So when dad ran out of gas for the lawnmower, he just we had a short piece of hose hanging up in the garage, and would go over to the truck and shove it down the gas tank, and he would siphon water out of that gas tank, or siphon gas out of that gas tank into the 5-gallon gas tug. So water is attracted to other substances. We call that adhesive properties. Now think about this. We've talked about those structures inside of plants that transport materials. There's no pump inside of plants to pump water from the roots in the soil to a sequoia tree that's 280 feet tall. There's nothing in there pumping the water to the top of a sequoia tree to the leaves. No, it's the leaves at the top lose water through transpiration or evaporation. That creates a suction on those xylem and phloem straw-like structures inside of the trunk of the tree. And that's how water is moved from the roots in the soil to leaves 200 feet, 280, 300 feet high. They don't drink when it rains. There's nothing pumping that. It's simply the adhesive properties of water that cause them to attract to other substances. You remember this from high school chemistry or high school science when you pour water or a substance into a graduated cylinder to measure volume, and there's a meniscus at the top, a concave meniscus at the top where you're trying to measure, and you always measure where? At the bottom of the meniscus, because water tends to crawl up the side of capillary tubes. When we draw your blood, we just touch a little capillary tube to a drop, and it literally sucks it up into it. All of that is because of these adhesive and cohesive properties of water. Now that takes us to another step here, where because of these adhesive properties of water, almost everything dissolves in water. Water is the universal solvent. Things that are dissolved in water are called solutes. But water, because it's attracted to other substances, anything that's dropped into it, whether it's salt or Alka-Seltzer or medications, hey, even steel at the bottom of the ocean will dissolve, rust over time. It could be metal in salty environments, air environments. It tends to dissolve. Limestone in caves dissolves over time. Solid rock will dissolve in water over time. What's because water is, because of its adhesive properties, almost anything will dissolve in water. It's the universal solvent. It dissolves what we call hydrophilic or water-loving substances. Many solids, ions, liquids can all be dissolved in water, and biologically very important for us. And so keep track of all of these characteristics of water, the cohesive properties, the surface tension properties, the adhesive properties, the ability to dissolve other substances, the solvent properties. The solute is the substance that's being dissolved in water. A solution is where you can't tell the difference between the solvent and the solute. Sugar in water, salt in water, any other substances that can be dissolved in water. A solution is where you can't tell the difference between what was dissolved and what's doing the dissolving. So understand the difference between solvents, solutes, and solutions. In this case, sodium chloride is, 77% of the Earth's surface is covered by marine water, saline water. So we have to talk about salt. If you've ever swam in the ocean, you know what we're talking about. It gags you. It's so salty. But it's because it's dissolved in water. Water tends to disassociate the sodium and chlorine, creating a very salty environment. This is, again, maybe biologically, maybe one of the most important environmental characteristics of the water molecule. Because of this strong attraction, this cohesion between water molecules, it takes an enormous amount of heat to heat water up, and it takes a lot of cold to cool water down. If you remember from your high school and junior high science, we call that specific heat. Specific heat is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. Now, that's not a lot of heat. 1 gram, 1 degree. But if we take all substances, liquids, solids, everything in between, water has one of the highest specific heats of any natural compound known. It takes a lot of heat to heat water up. It takes a lot of cold to cool water down. That is extremely important if you're an organism, if you're a critter that lives in water environments. And it covers over 70% of the Earth's surface. So there are a lot of critters that rely on water temperatures. Water regulates temperatures. It moderates heat gain and it moderates cold temperatures. So if you're an organism living in these environments, it's extremely important. You know this. If you're a fisherman, you know that if the water's surface close to the surface is warm, well, they just go a little deeper. If the water's cool, they just go a little higher. And but these water temperatures, they tend to moderate the body temperatures of organisms. Whales, dolphins, porpoises, sharks, large invertebrates. They rely on this property of water, that it doesn't simply change temperatures rapidly. One of the highest specific heats of all compounds, all because of this cohesive nature of water molecules. Very important. And really, one of the last couple of things we want to talk about is in the next chapter, we're going to talk a little bit about, or in the next section of this chapter, we're going to talk about what we call dehydration synthesis. If in nature and in our bodies, if we want to join some large molecules together, we simply remove some water. We dehydrate it. That causes large molecules to bond to each other. On the opposite, if we want to break down large molecules, we add water to it. We call that hydrolysis. So that's how important water is to the making and the assimilation and the breakdown of large compounds. We're going to talk a lot about that in the coming weeks. We either dehydrate and remove water, and that causes an attraction between large molecules, or we add water and that causes the breakdown of large molecules. So what we call dehydration synthesis or hydrolysis. We're going to hear more about that in the coming weeks. The last thing we need to talk about here for just a few minutes is the pH scale. Since so many things are dissolved in water, it tends to create either slightly positive charged solutions or slightly negative charged solutions. Things in our body like a little bit of a balance there. They don't like extremes here of these solutions. You know this is the pH scale. It's a scale that measures, okay, the extreme positive or the extreme negative solution types. And you know this is the pH scale. It ranges from 0 to 14. Higher numbers, even though we're going down here, higher numbers are basic solutions. Lower numbers are acidic solutions. You know this from common social media or just media. You tend to know what are acidic things and what are basic things, and you kind of know what's in the middle, what is neutral. Just plain water is about 7.0. That means there's not really a negative or a positive charge to the solution. It's rather neutral. Acids on the upper end of the scale here, or the lower numbers, they tend to have high concentrations of what we call hydrogen ions. Now, you can tell what's happened to this hydrogen. Take a minute and look at it. It's a hydrogen that has a positive charge. It's lost its one and only electron. So it's simply a hydrogen nucleus of a proton is all it is, one proton. So solutions that have high concentrations of hydrogen ions, they tend to be acidic. The more hydrogen ions they have, the stronger the acid. The human stomach, very high pH, very low pH, high acidic, high concentrations of hydrogen ions, a pH of about 2, which is really, really strong acid. Hydrochloric acid, some of the stronger acids, sulfuric acid, some of those stronger acids. But in the extreme of the pH scale here, the more hydrogen ions in this solution, the stronger the acid. On the other end of the scale here, these are basic solutions, sometimes called alkaline solutions. Basic solutions have high concentrations of hydroxide ions. Basically, look at this and think about what's happened here. It's a water molecule that has lost a hydrogen, but the oxygen has held on to its electron. So we'll call it a hydroxide ion, slightly negative because it's gotten rid of or kicked out the hydrogen proton and kept its electron. Solutions that have high concentrations of these hydroxide ions are strong bases. And the more hydroxide ions they have, the stronger the base. Look at some of these down here, some of these classic household items. But look right here in the middle, around 7, 7.2, 6.8. These are things that are neutral. In other words, they're basically H2O, a balanced out molecule. Look at this, human blood, about a 7.1 pH, very neutral. When that food comes out of your stomach with a very low pH, very strong acid, we have to do things to bring that back closer to normal. That's where things like the bile ducts come into play. You've heard of your gallbladder. Well, that's what your gallbladder does, is it pours bile into the small intestine as soon as it comes out of your stomach, so that it brings that pH up back closer to normal, so that when we send it through your small intestine, it's more of a normal pH. So this is the pH scale, measuring the strengths of acids and bases. But more specifically, I need you to know it's measuring the presence of hydrogen ions in a solution or hydroxide ions in a solution, the pH scale. We do 7 is about neutral. It's, generally speaking, water is pretty neutral. Blood is pretty neutral. We want the pH in most parts of your body to be pretty neutral. Things get a little bit out of whack when they get out of that neutral zone. But we do this when pH gets a little too high, we simply add more hydrogen ions. When it gets low, we add hydroxide ions. So those are called buffers, and we tend to buffer solutions that way. Hey, that's all I want to talk about right now for this section on chapter 2, but there's going to be another section, the final section of chapter 2, very important, and some information that you're pretty familiar with here in the next section of chapter 2.